Well, let's start with the idea of early stopping, where we keep going down, but we stop before the tree gets too complex. So how does that work? Simply recall that as we add more depth to the tree, we're increasing the complexity of the model. And so if we are avoiding this super complex models, then we can just avoid very deep trees. So the first early stopping condition is absolutely simple. Just limit the depth of the tree. Now, we know that the training error goes down as you increase the depth of the tree, but the true error goes down and goes up. So maybe there's some magical max depth where before that, the trees are simple, they get to good true error, but after that, the trees get too complex and the true error keeps going up. And so somehow, this max depth is going to be a magic parameter that we're going to provide where we stop going down the recursion once we hit that max depth. And just like any other magic parameter in machine learning, you have to figure out how to pick it. And the answer is validation set or cross-validation. Never use a validation set. No, sorry, never use your test set to pick your magic parameters. So this is what you have to do with max depth. Limiting the depth is just one approach for limiting the complexity of the decision tree. However, if you limit the depth, you're cutting every branch in the same way. But some branches might want to go further than others. So let's take a look at an approach where some branches might go down further than others. So for example, we can stop recursing if the classification error doesn't get better. So we split on credit, and now we're looking at what happens if we recurse some poor. So of the 5 safe loans that we have in poor, with credit scores poor, and the 16 risky loans with credit score poor, if we just stopped there and made no splits, we'd be making 5 mistakes. The error would be 5 out of 21, which is 0.24. Now, if I were to try to split on the other features, term and income, suppose that neither of them helped. Suppose that neither of them decreased the training error. So training error were still 0.24 for both of them. What should I do? Now I could try to split on one, then keep going, but that will make the tree more and more complex. So a second early stopping condition we might use is to say, stop there. If the training error is not decreasing, don't make the tree more complex. Use Occam's razor and stop the process right there. And just say, everything after credit goes poor is just a risky loan. And then just focus on what to do with the node where credit is fair. So the second type of early stopping criteria we're exploring is keep recursing, but stop if the training error does not decrease. Don't make the tree more complex. Now, there's a few practical caveats about this. First, typically you don't just stop if the error doesn't decrease at all. You put a magic parameter, you say stop if the error doesn't decrease by more than epsilon. Let's say if it doesn't decrease by more than 1%, you just stop. Then there's a few pitfalls in practice for this rule, and we talk about those a little bit in the context of pruning. So this is a rule you should be super careful about, but it's very useful in practice. So something to definitely keep in mind. The third type of early stopping rule is extremely important, and you should always include it. And it just says, if there's only a few data points left in a node, don't split any further, because then you're really risking overfitting. So in the example we've been looking at, we had that case where credit is equal to fair. Well, there was only 1 safe loan there and 2 risky loans. So total of only 3 data points fall inside of that node. In that case, if I were trying to split further, I'm going to find lots of patterns in the data that don't make much sense because there's very little data to support those patterns. With 3 data points, I don't know if I really trust a decision tree algorithm to make tons of decisions. So I'll just stop recursing right there. In general, we should always set kind of a parameter, say n-min, which says if a node has fewer data points than n-min, or n-min or less, then just stop recursing right there and call that early stopping condition 3. This one you should always implement, no matter what. For example, here I'm suggesting setting n-min to 10. 10 is quite a nice number for nmin if you have a relatively small data set size. If you have a huge data set size, you might set it to 100. But somewhere between 10 and 100 is a good value for nmin. So let's summarize the early stopping conditions that we described in this approach to try to find decision trees that are not too complex. There are three. The first one is limiting the depth of the tree. That's a relatively good condition to set, and you should set that one to be something pretty carefully using cross-validation. The second one is stop recursing if the classification error doesn't decrease by enough, decreases by zero, or doesn't decrease by more than epsilon. It's a little risky, but can be very useful. The third one, extremely useful, you should always do it. Stop recursing if there's not that many data points left inside of a node. So these are some of the key early stopping conditions a decision tree algorithm should be thinking about. If we go back to the decision tree greedy learning for decision tree algorithm that we discussed in the previous module, we started with the empty tree. We selected a feature to split on. Then we said stop if there was nothing left to do and just make the prediction. This is the majority class. And otherwise, we're going to recurse and go back to step 2. Now, we considered 2 stopping conditions in the previous module. And to those, we're adding the 3 early stopping conditions that we just described. And so a small modification to the code you've already built gives you this extra factors that help prevent some overfitting.